We've talked about two types of measurable quantities so far in this course. We've talked about scalars and vectors. And that's a really small pen, makes that look really terrible. Scalars and vectors. And a scalar is just a number, like time, like mass. And a vector has magnitude and direction. Those are things like, so let's do this. Mass, time, number of things. So if we talk about number of molecules, which is similar to mass. And vectors are things like length. Clearly I can't spell. Vectors are things like length. So far that's it, right? Length is a vector. Turns out area is also a vector, but we'll talk about that. We'll probably talk about that in physics too. So displacements. So if position is a vector, displacement is a vector, velocity is also a vector because it has direction. Acceleration is also a vector. Right? When we talk about the acceleration due to gravity, it's 9.8 meters per second squared. That's the magnitude. And the direction is down toward the center of the Earth. So I want to talk about how do we add vectors and what are various ways to represent that. So one simple way to represent a vector is an arrow, right? There's an arrow. Because an arrow has a length and it has a direction. So let's call that a specific vector. Let's call that like A. And how do I know A is a vector? Well, often we'll put a little hat on it, a little arrow hat on it. So that's vector A. And I could have, let's do another vector. We could do like vector B. Why not? I meant for that to be blue. Vector B. So I know how to add scalars pretty easily, right? Scalars just add the way you learned in grade school. But vectors add differently. Because sometimes when you add two vectors, you get a bigger answer. Sometimes when you add two vectors, you get a smaller answer. And that's weird. That's like saying I've got 2 apples and 3 apples. And somehow there's a funny way to add them to end up with -1 apples. So clearly, number of apples is a scalar because it doesn't add this way. But displacement is a vector, right? So I could say, I walked to the end of the street and I walked halfway back. What's the net displacement? Well, it's halfway up the street, right? Even though the path length was more than the length of the street. Okay, and that kind of describes exactly what I'm talking about. So let's say A and B really are displacements, right? They wouldn't have to be. They could be velocities, they could be accelerations, and those add the same way that we're going to talk about right here. But displacement is really easy to visualize. So let's say I walk path A, right? I walk path A, and I don't like that. Here, let's move that over here, and then I walk path B. How far have I walked in total, right? Not length, but what's my total displacement? Well, if I did A and then B, I'm starting B at the end of A. So I need to move the tail of B to the tip of A. All right, and then my net displacement, let's make it purple. I like purple. Then my net displacement would be this vector right here. So that vector is A plus B. Right, and this is the way to graphically add vectors. It's not the only way to add vectors, but it is a good way to get a gut instinct of what the answer is. So if I want A plus B to equal, C, why not? Then this is C. I can add them tip to tail. Right? So you take the tip of one, add to the tail of the other. And it doesn't matter which one you put at the tip and which one you put at the tail. Let me demonstrate that. See if I can do this in a clever way. So if I move that off, I could let me move these out of the way a little bit because I want to show you something kind of cool. Let's just do this. Let's do this. What if I put B, just copy it. Boom, there we go. Okay. So, just move that down a little bit. So now I've got A and B again, right? Let's move that out of the way. If I wanted, I could move there. Now I've got them separate. I could move B here. Bear with me. I've never been able to copy arrows before, and this is kind of exciting for me. So I could say, well then, the answer to this addition problem, right, was tip to tail, and I had, no. This guy, nope. This guy was B, and this guy's A. So when I said I walked A and then B, my answer was this vector right here, right? But what if I walked B and then A? Well, that would be exactly this, right? This one's A, and this is B. But look, if I draw the tip to tail for that guy, we're almost there. It's the same darn thing. We've drawn a parallelogram. Do you see that? So when we add vectors tip to tail, it does not matter which order we add them. You know what that is? That's the commutative law of addition, right? That means A plus B equals B plus A. All right, so that's great. Addition of vectors is commutative. Turns out only some kinds of multiplication of vectors is commutative, but we're not going to get that far into vector math in this course. So I want to talk about a couple examples here. So we have some vectors below, A, B, and C. Let's add them together. Or let's do some math with them, right? So I have tried to copy these. It doesn't work. So maybe that's a blessing. Maybe that's a curse. It's fine. It's fine either way. All right, so how do I add A and B? Well, this is actually kind of nice. A and B are in the same direction. So they really do add. If I had sizes for these, if they were 3 and 2, the size of the answer really would be 5. But this is a special case, right? There's A and there's B. And the answer here is tip to tail, right? It's the tail of one end, so that's like right here, and the tip to the other end, that's right here. So we added these tip to tail, and that really is, go over here. There we go. That really is the answer, D. What about if I subtract them, right? A minus B. Well, I'm glad you asked that. So how do I subtract them? Well, it turns out if we think critically about what a negative sign does to a vector, negative B, let's do this in some scratch space over here. Negative B is just B that points in the opposite direction. And that's a little gross. I can do a little better than that. Not a lot better. So that's negative B. That's what negative B is. So A minus B is the same as A plus negative B. So we already know how to do this, because now I know what a negative sign does. Now I know what a negative sign does. So I can just say, well, A goes this way. There's A. And B, if I go tip to tail, I start B where A ends. Goes this way. So there's B. Really, it's minus B. So A plus minus B is this vector right here. There's D. Right? And again, we can say, if I walk A and then walk back B, my total displacement is D. Great. Let's look at A plus C. A plus C. Well, C is now this off-axis vector, right? It's not pointing along the same direction as A and B. So now our addition is going to be a little more non-standard, but it's still tip-to-tail addition. We can still do that. So A is this vector. And I'll just start C at the end of A, and it goes back kind of like this. There's C. I think I intended C to be the same length as A, just a different direction. So the answer then starts where A starts and ends where C ends. That's D. Right? So if A and C are the same length, here I have a sum where the answer is actually shorter than either of the things going into it. Isn't that weird? Right? Again, this is like saying I've got 2 apples and I've got 2 more apples and they're adding to 1.5 apples. Well, no, because apples don't add that way. But displacements do, right? Velocities would. Let's say I have 2 rockets, right, mounted on me that one fires off to the right and one fires off well, if it fires to the left, let's say it fires to the left so that it gives me a thrust to the right, and the other one fires up and to the right so that it gives me a thrust down and to the left. The net thrust would be D. All right, so thrust is actually a force, and force is a vector. Anyway, I want to skip D here, part D, just to give us a little more time in this video. Let's talk about a shortcoming here. So the benefit of graphical vector addition is that you can draw it out, right? You can sketch it out, you can visualize it. It's very good for hands-on and for getting a gut instinct of what your answer should be, generally. But unless you're drawing very carefully, this doesn't do a great job of giving you a quantitative answer. And that's where vector components come in. So I want to introduce vector components. So let's go down here a little bit. So what are vector components? Well, I can take some vector, let's say this guy. That's really big. Make that a little smaller. There, perfect. No. I can take some vector, call it A, why not? And I could say, well, that looks like it points up and to the right. Well, how much does it point up and how much does it point to the right? So I could decide, because I'm choosing up and right, but I could decide, let's actually put some axes on this, and let's put the vector at the origin of the axes. So here's a y-axis. No, it isn't. Try again. There's a y-axis. And then I'll put an x-axis here. 0 degrees, please. It's so close. Ha! There we go. And here's an x-axis. Great. X and y. And now I can ask how much of this vector A points in the x direction and how much points in the y direction. Well, I could see, like, look. So this much points in the x direction, and there's a little bit of delay there. Like this much points in the y direction. So this would be like A sub x, and this would be like A sub y. And if I knew the relative angle of A to these axes, I could solve for exactly how big AX and AY are. So let's say I know theta. right? So if I know magnitude and direction, which is 2 bits of information, I could find AX and AY, which are 2 different bits of information but describe the same thing. All right, so that's actually important to remember that a vector needs at least 2 bits of information. And in fact, you need 2 bits in 2D. You need 3 bits in 3D. All right, but we're going to do everything in this section of this course in Physics 1 and 2D. When you get to Physics 2, you have to think about 3D a little bit. Okay, so how do we relate those mathematically? Well, SOHCAHTOA, right? And I brought up this, where are you? Trig reminder. Hey, look at you. All right, so the hypotenuse here is the length of the vector, right? That's the magnitude of the vector. And the adjacent part is the x component, and the opposite part is the y component. All right, so it looks like I'm going to use sine for y and cosine for x. That is often true, but not always. All right, if you define your angle, let me go back here. If you defined instead of theta, I'll just mark this, why not? Instead of theta being this angle, please let me mark on you. Nope, okay, fine. Instead of theta being the angle to the x-axis, theta could be the angle to the y-axis. Oh, it's in the scratch page. Sorry, guys. Right, I could define this angle right here. And if this is the angle I use, let's call it phi, then sine and cosine are reversed. Okay? So all I'm saying is it's worthwhile to think through SOHCAHTOA every time. All right, so, okay, ka is opposite, ka. It's adjacent over hypotenuse, right? So cosine of theta is adjacent a sub x over hypotenuse, which is a. Right? Often I'll rewrite this as a sub x equals a cosine theta. All right? In fact, I'm just going to do that because we rarely ever use it in this format. Okay. So a sub x is a cosine theta, and a sub y is a times sine theta. Again, only true if theta is defined relative to an x-axis. If it's defined relative to a y-axis, it reverses sine and cosine. But if you just think through SOHCAHTOA every time, you're in the clear. Again, this relates our 2 bits of information, magnitude and direction, or x and y components. Let me give you one more bit here. I can go backwards, right? If I knew ax and ay and I wanted a and theta, I can remember that a squared plus b squared equals c squared. So this is a right triangle, right? As long as I'm using orthogonal axes, meaning x and y directions are perpendicular to each other, ax and ay will always be perpendicular, and I can always write this. That's ax squared plus ay squared equals a squared. All right, Pythagorean theorem shows up everywhere. The other thing I can say is if I knew ax and ay is also over here, so that's the opposite, and this is the adjacent, that's a tangent. So I could say theta is the arctangent of ay over ax. Okay, that's pretty useful. So let's see how this affects vector addition. All right, so let's take a couple vectors. Let's say 5 meters that point straight up. Sure. And 4 meters that points off at an angle. So let's put that, I don't know, like here. That's pretty close to 4 meters, sure. And let's say it points off, relative to the horizontal, it points off at an angle of 30 degrees. And I could call these vectors A and B. I could call them Hank and Susie, but A and B is a little more concise. Again, they're just labels, right? I could draw a tasteful picture of a cat and call that my label for the vector, but letters are convenient. Okay, so let's say I want to know again, what is A plus B? Well, clearly I could add using graphical vector analysis, right? I could put 4 meters right here. There's my 4 meters. This angle, again, is 30 degrees. And it looks like my answer is going to point off like this. Something like that, right? So, but really, what can I say? Up and to the left and longer than 5 meters, but shorter than 9. If I'm very careful, I could measure this with a ruler and get pretty close. But what I'm suggesting is if we break 5 meters and these two vectors, A and B, into X and Y components, I can just add their components, right? Think about it. I go 5 meters north, and then I go part of 4 meters north and part of 4 meters west, right? Well, north and west, those are just X and Y, right? Or negative X and Y. So let's break these into components, and let me give you this. What I just told you verbally is just this. So let's let the answer be C, right? So C sub X is just A sub X plus B sub X, and C sub Y is A sub Y plus B sub Y, right? And I can see pretty quickly A sub X is 0 and A sub Y is 5. B sub X is something negative and B sub Y is something positive. So A is pretty easy to break into components. B I'm going to have to think a little bit more about, but it's just trig. We can do it. Okay, so let's write this down, right? A sub X and A sub Y. Again, A points completely in the Y direction. Let's put some axes on here so that we can be for sure clear. So X is to the right, and A does not point to the right at all. So that's 0 meters. And Y is completely 5 meters, and it's up, so it's positive. Let's do B sub X and B sub Y. All right. I can actually see, like I said, I like to just draw the right triangle. So B sub X is this thing, and B sub Y is that same thing. So here's B sub X, here's B sub Y. B sub Y is definitely positive. B sub X is to the left, so it's negative. And it looks like X is adjacent, which is cosine. So let's do that. So B sub X is B times cosine theta. B sub Y is going to be B times sine theta. And I didn't leave myself much space, which would normally be a problem, but thanks to technology. Okay, so B is 4 meters times cosine of 30 degrees. And what I get is 3.46. But look, it points to the left, and my calculator didn't give me a negative sign. It gave me a positive sign. That's because the calculator thinks it's a triangle. He said the calculator thinks. Well, I mean, for a triangle, that it doesn't use negative signs. You could put a negative in there in the calculator, but I prefer just to think about the triangle and then put the sign in manually. All right? And if you notice, I did make a mistake there because I was talking. There, it's a negative sign. Okay, so we'll remember that. And then 4 meters times sine of 30 degrees turns out to be exactly 2. Okay, now we're ready to add these together, and we're going to get a precise answer, right? We're not going to get something hand-wavy. So let's do this. So then CX is AX plus BX. And AX, remember, was 0, and BX is negative 3.46. So this is negative 3.46 meters, which tracks, right? If you go back to the original problem, or the original, like the drawing here, all of the x motion comes from B, and it's to the left, so it's negative. So that tracks. And CY is AY plus BY. Remember, AY is 5 meters, that's all of it, and BY is only part of it, it's 2 meters, so that's 7 meters. I didn't even have to plug that into a calculator. I'm that good. Okay, so that's our answer, right? CX plus CY. In fact, I could plot those on here. I could say, look, here is CX, and here is CY. CY is big and positive, which is positive 7. CX is smaller and negative. That's negative 3.46. Great. So let's do one other thing with this, and we'll call it good. And that is, what if instead of the x and y components of C, I wanted to know magnitude and direction? Well, the magnitude is just going to be cx squared plus cy squared. So I can do Pythagorean theorem again, right? If you do this, right, so we plug in minus 3.46 meters squared plus 7 meters squared is c squared. What I get for c, the size of c, is, I haven't worked that yet. So, 7.8. Okay, that makes sense. It should be longer than 7, but not a whole lot longer. Okay, so the length of that is 7.8. That makes sense. It's less than 9, like we said. It's bigger than 5 for sure. Quite substantially bigger than 5. So then what am I left with? Sorry for all the motion here. Hope you don't get seasick. I want to know this angle right here. So it looks like I could probably do some geometry on this to figure out from this like polygon. But you know what? I'm just going to use the arc tangent of y over x. So the angle here is the arc tangent of cy over cx. But I'm going to do one thing with it. I'm going to do an absolute value. And here's why. I drew this right triangle here. I want to find this side, and this angle right here, and if I plug in a negative sign, it's going to give me some other angle, maybe this angle, or an angle below some other axis or something. And I just don't want to depend on myself knowing trig that well, to be honest. But I know right triangles. If I know right triangles, then I can just do things pretty well. And so what I'm arguing is that's why I'm ignoring a negative sign here. Okay, so let's plug in. We're almost there, you guys. Okay, so cy, the absolute value of cy, that's 3.46 meters divided by 7 meters. What I get when I plug that into my calculator, let's see. I get 26.3 degrees. And that is wrong. Ooh, yeah. So this is a good reason that we gut check our answers, right? Because this looks like it's bigger than 45 degrees. It does not look like 26 degrees. What did I do wrong? I inverted these. I reversed my y and my x. So, again, let's erase that and fix it. There, 63.697, let's call it 63.7 degrees. There we go. That looks right. Okay, so the first step of any physics problem is draw a picture. The last step of any physics problem is, does your answer make sense? Because mistakes happen. So, thanks for watching.